Okay. Hello, everyone. Good morning. Hello, Chair, everyone. It is great to see you. Today we'll have the second day of the Rocling 2022. I'm Yu Cao from Academia Sinica, Taiwan. And it is our great pleasure to have invited Professor Junichi Yamagishi Sensei to give us a talk about speech synthesis research 2.0. Let me briefly introduce Professor Yamagishi. Professor Yamagishi received his PhD degree from Tokyo Institute of Technology, and he is currently a professor of National Institute of Information and Informatics, and he is also an honorary professor in Edinburgh University. His research interests include speech signal processing, machine learning, media cloning, and media forensics. And he's a world-renowned speech synthesis researcher. If you are working on speech synthesis or voice conversion, you must know him. And actually, he's also very famous in speech enhancement field. Maybe he doesn't know that because a database he collected is become a benchmark in speech enhancement, okay? And he's an organizer of many important events internationally. For example, ASV Spoof and Voice Conversion Challenge. And recently, I'm very honored to co-organize with him on a Voice Mouse Challenge. It's the goal is to predict the quality of speech signals. So if you are interested, you can go to find the project, Voice Mouse. So today is our great pleasure to invite him. Let us give a big hand to welcome him to give us a talk.
Hi, so good morning, everyone. So thank you very much for the very kind introductions. My name is Junichi Yamagishi. Professor Yu Cao already explained my background, but I just want to quickly introduce myself a little bit within 1 minute. So I spent most of my early careers in UK as a University Edinburgh, then work on several UK and the EU projects where we focus on speaker ID. I'm interested in speaker IDs. For instance, can we create our personalized voices, but in different languages for speech-to-speech translations? Meaning, can we generate audio with my voice, but in French or in Chinese, for instance? I also work on similar idea, but for people with vocal impairments. Some people may, lose their speaking ability due to their, vocal problem. So if it's possible to do digital cloning of their voices before they lose their speaking abilities, it might be possible to create, new type of assistive devices. So that was the voice banking project, which I did in UK, which also becomes a startup called Speak Unique. Recently, I'm working on protections of such technologies. So meaning that if it's possible to do digital cloning of someone's voice, but without your permissions, that might become a problem because we can create so-called deep fakes. Luckily, I was able to write the proposals before these issues becomes critical in our daily life, and then I got funding from the government to do such a project. I also quite keen to create database and tools, as Professor Yuta already mentions. Maybe you might see some of the databases I created, such as VCTK database, voice bank database. This is the ones used for speech enhancement. Voice Mouse dataset. This is also a large-scale database to predict subjective quality of synthesized speech. And then HTS toolkit. This is old toolkit, so probably nobody uses anymore, but this is a toolkit for using hidden Markov models to build speech synthesizers. And then some security, speech and the security database called ASP-spoof. And then I have some small computer vision team in my group, and then they also develop tools called Mesonet, which is quite popular deep fake video detections. I also have small NLP teams in my group. Then, like our first keynote yesterday, we're also working on automatic fact checking. So if you go to our GitHub web page, you can find pre-trained models trained on the famous database called FIBA. Unlike first keynote speaker, we are working on NLP side, so rather than information retrieval. So our focus is like language models, but this model is also frequent to use a baseline. Then in my talk today, although we are working on various topics, including speech, computer visions, and text, I will focus on speech, especially speech synthesis, because the current situation on speech synthesis is quite interesting because the quality of synthesized speech reaches almost human level quality. And then some people say that fundamental problem of speech synthesis has been solved, which is good news because speech synthesis history has over 70 years, and then we haven't had such a situation before. But as a researchers, we have to consider next steps. So I want to show some of our new attempts. Given such a high quality speech synthesizers, can we use a new application? Can we create new applications for entertainment? Can we create some new communication technologies? Also, can we use such a technology for our own privacy? So that's part one and the part two. So in the part one, please let me explain the current situation of speech synthesis. So as I said to you earlier, quality of synthesized speech has been almost natural speech as human, but probably you might not believe. So let me show you some evidences. But before I show you such a statistical evidences, let me quickly explain two main streams for speech synthesis called text-to-speech and the voice conversions. They are quite similar each other. The difference is basically input. So for the text-to-speech, we use a text as an input. Then for the voice conversion, we use a speech of somebody else as an input. Then we transform such inputs into target acoustic features, which could be male spectrogram or some vocoder parameters. Then we have waveform generations to generate low waveforms. Then output speech should sound the natural speech and also intelligible and also should be similar to target speaker. So it's quite a similar framework. Then, as I said, quality of both text-to-speech and voice conversion is good. So let me show you such a sample and the listening test result to convince you. So here, I prepared audio samples of human voice and also synthesized ones using Google's Tacotons 2 with neural vocoders called WebRNN. The left one is a human and the right one is a synthesized one. Of course, those samples are not included in training database.
We did not compete with any other local farmer. We did not compete with any other local farmer.
Employees are entitled to follow their contract to the letter. Employees are entitled to follow their contract to the letter.
At that time, there was no infection within 5 miles. At that time, there was no infection within 5 miles.
So please know that this is the samples created in 2019. Then quality was so amazing. So we decided to do large-scale listening tests to benchmark this new framework and also other available system at the time, including voice conversion system with 1,000 listeners to see whether human can tell the difference between synthesized ones from human ones. I will not explain the details of all the system we use for the listening test, but we collected many variants of speech synthesizers and voice conversions. Then here's the results of listening test with 1,000 listeners. The first box plot shows the results of the naturalness, and the bottom one shows the results on the speaker similarity, how similar the synthesized speech is compared to the target speakers. Then so we have target speakers as well as non-target speaker, but human. So those two should be rated as natural. On the other hand, those non-target speakers should be rated as dissimilar, different from target speakers. And then we could see this point. Then one of the systems called A10 that has very high score. Then compared to the natural speech, there was no statistical differences. P-value was the 0.012. Then that's also the case for speaker similarity. P-value was larger than 0.1, meaning that there's no difference between natural speech and synthesized speech for A10. Of course, if you look at other systems, there's a huge difference. So this is a good news. Then the next year, I decided to do similar benchmarking for voice conversion system through voice conversion change. We compare the system, various system built by 33 organizations. They kindly built various voice conversion system shown here using same database. So I recruited 200 subjects again, and they compared the naturalness and the synthesized speaker similarity of converted speech. Then, according to this voice conversion change, 2020 to 2020, in terms of naturalness, there's small difference between human and
In reality, the European Parliament is
top system. But in terms of speaker similarity, there wasn't statistical significant difference between human speech and converted speech. And also, surprisingly, such situations happens not only top system, but also top eight system. So meaning that within the 1 year, technology becomes much nicer, and not only the tacotone and the wave RNA combinations, but also other systems manage to reach the goal for voice conversions. So it's quite surprising. So let me play some sample. So this is the source speaker samples.
In reality, the European Parliament is practicing delay tactics.
The target task is to convert her speech to target speaker, and the target speaker sounds like this.
In reality, the European Parliament is practicing delay tactics.
And the converted one sounds like this.
In reality, the European Parliament is practicing delay tactics.
So if you're interested, you can go to zenodo.org and you can download all submitted speech. Listening test data is also available. The point is, I think the part of the fundamental problem of speech synthesis and voice conversion has been solved. So I think as researchers for fundamental research, we have to think of what we can do next given this natural speech level speech synthesizers. Then of course, we don't know perfect answers yet because that's new challenges for us. But we come up some 3 interesting ideas. Then let me show you such applications one by one. The first one is called rakugo speech synthesizers. So rakugo is written in Japanese like this, which is basically entertainment applications. So we want to develop speech synthesizers that entertain listeners. That's automated code. So why Rakugo speech synthesizers? That's, as I said, I think just conveying the message to the listener has been solved, and then we have solutions. But as you know, speech can also entertain listeners, but current AI cannot do that. Then, in my opinion, Japanese traditional vocal performance called rakugo, which is kind of like a stand-up comedy, but traditional ones, is a good example because professional performers use a very variety of vocal expressions to imitate various characters in the story and then entertain listeners. So this is a good example to see whether AI or speech synthesizer can entertain people or not. Then we decided to challenge this. So the ultimate goal is to create AI storytellers in entertainment applications. If you don't know rakugo, I think you can find many places in Japan. So there are many places where you could see the rakugo in Japan. Then he's one of the professionals such as rakugo performers. So he sit down on the stage alone, and then he will explain stories. The stories are in two categories. So one of them is called Edo rakugo, which is a classic rakugo established in by old, like 1920s, and the new ones, new one, it's new, it's old, it's the 1930s. Then in this studies, we use classic rakugo called Edo rakugo because somehow stories are already determined. Of course, the performer will do some arrangement, but most of the story lines are fixed. So it's a good target for us because we don't need to do story generations as you saw yesterday for the challenge. So we basically use a given storyline and synthesize speech. But the problem is we don't have data. So we decided to create rakugo speech database, which is quite expensive because we need to pay professional performers to do performance only for us in studio, but we have to do. So we convinced one of the highest ranked performer called Sanza Yanagiya to do the recording for us in studio. Then he kindly did the recording for us with 25 famous performance of Edo classic rakugo stories. The question is how to evaluate such speech synthesizers to entertain listeners. We cannot use a newspaper text. We have to use one of the rakugo story to see whether listeners can entertain or not. And then how can we do relative comparisons? That's another question. People could say that, I enjoyed this rakugo in, say, 4 out of 5 point scale, but I don't know what it means. So we decided to compare AI speech synthesizer, so AI or deep learning speech rakugo synthesizers with humans in various ranking. In Japan, rakugo storytellers are categorized into 3 different ranks: Shin-uchi, Futatsume, and Zenza. And then Shin-uchi is a top rank, and then this Futatsume is a second rank, and this Zenza is the lowest ones. So we decided to compare our models with humans, with in different rankings to see, which one we could beat with them. And then we decided to use the same story, including 1 long story and 22 short story. So it's not sentence by sentence evaluations, it's a paragraph level evaluations. In terms of architectures, we did serious modeling because our background is machine learning for speech. So input is text, of course, and the output is a mail spectrogram. In addition to that, we also need to model characters who appear in the story. So we use reference encoders to extract speaker embedding. Then we did some kind of like a clustering of speaker embedding so that we could run typical characters appearing in the story. Then we use this template as a dictionary of the characters. Then as a synthesis time, we have to choose one of them. Then we basically provide the grand truth. Then in terms of encoders, it's similar to tacotron ones, but we attach self-attentions and LSTM and so on. Decoder is an autoregressive decoders with two types of attentions, with forward attentions and additive attentions, just to make the trainings more robust. All right, then let me play some samples. Also, it's in Japanese. Let me play some of the sample for you.
それや、貞吉。ダー様お呼びでございますか。台所でもって豆を煮てるんだ、味噌豆を。煮えたかどうかちゅいとお前見てきておくれ。あ、この鍋だないしょはグツグツグツグツいって。グツグツいってんの分かったけど、見ただけじゃ煮えたかどうかわかんねえ。あ、ちょうどいいやしゃもじがあるから、一粒だけ。よいしょ。あっち、あっち。
Right, so this is a synthesized one. Then let me play performance done by top rank professional performance.
一席お付き合いをいただきます。おい、貞や、貞吉。旦那、お呼びでございますか。台所でもって豆を煮ているんだ、味噌豆を。煮えたかどうかお前ちょいと見てきておくれ。はは、この鍋だな。よいしょ。うわはは、グツグツグツグツいって。だけどな、グツグツいってんの。
Then in terms of second and the third one, it's painful to listen because it's not enjoyable too much. So let me skip the second and third ones. But let me explain the evaluation criteria. So we presented those samples to the listener and they asked 5 questions. Speaker is a human or not? Can you distinguish the role of characters? Can you understand the content of the story? Did you enjoy it? Which is most important questions. Also, have a skill of such a storytellers. That's the questions.
それや、貞吉。
Oops, sorry.
ダー様お呼びでございますか。
Then this is the result, which is a BC figure. So let me explain these results one by one. This is the result for naturalness, result for characters, character distinctions, and understanding of the content. And then this is the questions like, did you enjoy it? And this is skills as a rakugo performer. Then SS stands for speech synthesizers. N, S, NF, and NZ means a natural one, but with different ranking. So S stands for top ones, top rank ones, and F means second rank, and Z ones are lowest ones. Then, as you could see from these questions on naturalness, you could see the question naturalness is really high. Like Moscow is above the 4, which is a good news. But surprisingly or disappointingly, character distinctions was lower. Character distinctions of synthesized speech was lower than human performance, even the lowest rank ones. In terms of understanding, situation is similar because they cannot distinguish characters properly, so they cannot understand content perfectly. And then naturally, answers in terms of did you enjoy or not, and the score also becomes lower. Then, as a result, in terms of skill, TTS was rated lower than third rank. So meaning, of course, we have the room for the improvement, but so it was lower than even the third rank. So this is somehow surprising for us. So we decided to do some analysis why we got such a result. Then the first, we analyze correlations between each score for the listening test. Then we see that the questions on, say, enjoyment and the skills are more correlated with the content and character than naturalness. Meaning that if we want to improve a score for enjoyment or score for skill, we have to define character modeling and the content instead of naturalness. So that's one message that we could see from this listening test, which is actually quite interesting message because the speech synthesis research so far just try to maximize the naturalness. But actually, naturalness doesn't correlate with enjoyment or like a professional storyteller's skill. So if you want to improve these kind of enjoyment or skill as a performer, we have to consider other point, like human perceptions or other type of objective functions apart from naturalness, which is measured by, mean square errors, L1, or likelihood. We have to come up other objective functions. Another point that we found is speaker modeling and lack of speaker modeling. So we decided to visualize how human performer and synthesized models represent characters in the story. So in this figure, basically we extract X vectors from Zenza, Futatsume, and Shin-uchi by human, and also synthesized ones corresponding to two characters appearing in story, Sadakichi and Danna. So there comes some conversation between two. Then if we look at, say, lowest rank or second rank, we could see that there's two clear separations between X vector corresponding to characters, meaning that so basically rakugo performers simply change vocal characteristics globally. But if we look at top performers speaker embedding, there is no distinctions between two characters, interestingly. Meaning that, but of course, human can tell the difference. Although speaker embedding cannot capture such a difference. So meaning that human performance basically realize such a characters using not X vector like representation, but more like a micro movement, or maybe we don't know how, but they use a different way that X vector can capture. And therefore, our speech synthesizers use X vector cannot produce characters appearing in the story. So that's one point that needs an improvement. So how can we improve the character modeling for storytellers? That's not X vector, that's something else. That needs something else. But that's an ongoing topic. So unfortunately, I don't have the answer. But let me move on to the next topics, which is the communications. The previous topic was to use speech synthesizers for entertainment. Now I will use speech synthesizer for improving intelligibility of our speech in noisy environment, which is we call speech intelligibility enhancement. Then probably some of you who work on speech enhancement first wonder what is a speech intelligibility enhancement compared to speech enhancement. They are different. So please imagine situations with when you talk to someone with a Zoom. So when you talk to someone via Zoom or Google Meet, you have two environments, right? You have a remote environment as a talk where talker is speaking to you. Then this talker has some noise. Then here's the listener's environment. So listener will listen to talker's speech with his background noise, his or her background noise. But listeners also has noise in his environment. So left side is called far field environment, and then this sort of far end environment, and this side is called near end environment. Then the noise in this near end side can be suppressed by using speech enhancement technology before transmissions, but noise at our side cannot be transmitted, cannot be suppressed because noise is physically there, and therefore we cannot cancel such a noise. So in summary, there's two types of noises that are removable or non-removable. Then speech intelligibility enhancement focusing on the noise that's non-removable. And therefore we have to transform speech so that it sounds more intelligible in noisy environment. So it's kind of like a voice conversions, but we want to transform speech so that it sounds more understandable in noisy environment. Then simple solution is making louder, but if we make it louder, I think that makes people annoying. Therefore, we want to enhance the intelligibility of speech without increasing the volume. So that's what we want to do. Then this is not just supervised training, because unlike speech enhancement, where we can easily collect clean speech, also target speech, input speech by adding the noise, and then we can do like a basically regulation between noisy speech and clean speech. We don't have perfect intelligible speech, or mostly speaking. We don't know what is the most intelligible speech in advance. Therefore, this is not simple supervised training. Then basically I borrow the idea from metric gun proposed by Yutao's group, and then I formulate a task as a transforming speech so that transformed speech has a highest maximum intelligibility score in noise. By defining task in like this, basically we could use similar framework to metric gun, and then we can use training data also given noise to do these conversions. So this model is called iMetric GAN. Then I will explain the framework in the next slide. The iMetric GAN has three modules: conversion modules G, intelligibility evaluation modules D, sometimes called discriminators, and then true intelligibility functions Q. The role of the discriminator D is to predict intelligibility score calculated by Q in noise, rather than identify real, fake, or adversarial training. And therefore, the goal of discriminator is to approximate Q functions. Then given this Q, which is a good approximation for target intelligibility score, we train G next so that G can output speech that has a highest intelligibility score according to the learned matrix. The difference between these models and the original matrix GAN is generator accept both clean speech and the noise as the inputs. Then we also measure intelligibility score in noise rather than measuring the intelligibility score using enhanced speech. Then here's the details of the generators and discriminator if you're interested. And generator has the basically CNN. And in addition to 1D causal CNN, we also have energy normalization layers here because we do not want to make output louder, so we decided to constrain and normalize the output energy to be the same as the input. Then the output layer basically predicts constant values to multiply spectrum values represented by ARB filters. Intelligibility evaluation modules D has a 2D CNN, 5 blocks. Then these outputs, the intelligibility score, provided by to-do functions Q, which is not shown here, but they are normalized to values between 0 and 1. Let me quickly show you experimental results and conditions. So we trained these imetric models using 600 Harvard sentences uttered by 2 speakers in different genders. We also use noise in 3 SNR and 4 conditions taken from MSSNSD database. Then SNRs are -11, -7, -3. This is very challenging conditions compared to typical speech enhancement that typically use like a -5. So we interested in like a -11. And then intelligibility matrix approximated include the SIIB, HASP, and the E-STOI. In addition to intelligibility score, we also try to run quality score as a part of the output of the discriminators. They are PESC and BISQOL, which is ones proposed by Google. Then we did listening test to evaluate enhanced speech in noise. Then they are 120 Harvard sentences, and they, of course, they are not included in training databases. And the noise SNR also different from the ones included in training databases. Cafeteria, airport noise, -9, -1, -1 dB. For the airport, -13, -9, and -5 dB. In addition to noise, we also consider reverberations for testing only, test site. Then T60 values are shown here. Then we compare this system with 5 system, no conversions, and then SSDRC, which is the best system according to Harikate challenge. This is a simple DSP-based spectrum shaping and also dynamic range compressions. It's kind of a technique similar to one using music, making vocals louder. And then we compare several variants, including our old iMetric gun, which use a different intelligibility metrics for older ones, and then the new ones, but they use only intelligibility indexes only. And then the last one use both intelligibility and the quality scores simultaneously. In terms of subjective evaluations, we recruited 90 native English speakers. Then we asked them to transcribe what they heard, but only the content word. We asked them to ignore like a op or a. We ignore, exclude such a not useful words and just transcribe only the contents word. Let me play some samples. Here's the sample 1. with cafeteria noise. And the first one is an unmodified speech, and the next one is a converted ones.
We don't like to admit our small faults. We don't like to admit our small faults.
Let me play sample one more time. Probably in the first one, probably you couldn't hear any speech.
We don't like to admit our small faults. We don't like to admit our small faults.
Can you hear the male speaking in this very adverse conditions?
Bombs left most of the town. Bombs left most of the town.
I hope you could hear like a male speaking in this very noisy environment. Then the listener's task is to transcribe what they are saying. Then this is a correct answers. It's quite challenging. Then here are the results of the listening test. Since it has many information, so let me explain how to see the results first. So we have several bar figures here. They are the ones corresponding to different noise level and different reverberation degree. Then this one is the most challenging environment, like a more strong reverberations and the most strong noise. And this is the easiest ones, less noise and weaker reverberations. SNR is a -1, and then reverberations time T60 is 0.3 seconds. Then the message we could see from this figure is basically good news. And the first, the proposed methods includes a percentage of correctly transcribed keyword compared to the natural speech. This orange one compared to the gray one in all the conditions. If you focus on this one, easiest case, where SNR is a -1 dB and T60 is a 0.61, no, sorry, this one's. The keyword accuracy rate increase from, oh, sorry, this is wrong number. This should be this one's. 49.5 to 85.2, meaning listener was able to listen only half of the word, half of the keyword, but now they could understand 80% of the keywords, which is good news. Then this keyword accuracy was improved by using intelligibility matrix and quality matrix at the same time, and then we can confirm this by comparing this orange one and also blue ones. Then we could also see that which matrix is important by looking at this orange one and also green one, which is our old I-metric gun, because there's a huge gap between two. And the difference between these orange ones and the old one is which like a correct intelligibility score is used when we train I-metric scan. So we basically use old metrics like a STOI instead of E-STOI. Then the improvement obtained by using newer metrics. Then finally, by comparing proposed ones and also DSP-based ones, we could see the improvement as well. Here's the results for airport noise. The basically message is the same. This method works and help listeners to understand content work correctly. Then, since I show the pictures where basically far end and the near end environments are connected through some internet work, so we also decided to jointly optimize such a near end processing and the far end processing at the same time. Meaning, we decided to optimize speech intelligibility enhancement and speech enhancement modules at the same time. We have two types of noise, far end noise and the near end noise. That we provide both type of noises. So far end noise will be added to the far end speech enhancement modules, and then near end noise is provided to speech intelligibility enhancement. Then all of them are jointly optimized based on SISNR and also discriminator losses. And it works, although it's complicated. So if you're interested, please see these papers for details. Then in the last maybe 5 minutes, I will talk about another applications where we transform speech using speech sensitive framework to protect our own privacy, which is we call speaker anonymizations. The motivation behind this third topic is different from first and the second one. So please quickly explain motivations. Why do we want to use speech transformation technology for our privacy? That's because our voice is quite rich and contain many paralinguistic attributes like speaker IDs, ethnicity, pathology, age, and so on. And then some of the attributes like a speaker ID or ethnicity could be sensitive information. Then what happens if you don't care this is such a paralinguistic attribute? Since attackers nowadays can also use deep learning technologies quite easily, he or she might use some speaker recognition technology to basically to identify you by comparing his model output and also audio uploaded to the say SNS. So if you don't do proper protections and carelessly upload the audio, attacker may comparing such an audio with their database. Then even though we don't say our name on SNS, attacker may identify and review your name. That is a so-called de-identification attack in security field. Then this is what we want to prevent. Then does this happen? I think yes, and that's partially because attacker can also build such a attribute recognizers quite easily nowadays. What attacker can have to do is to just download basically pre-trained SSL models and then attach some additional one layers on the top of say Hubert, Web2Beck, and then just fine-tune them. Then that's it. Once after such a simple processing, basically attacker can build attribute recognizers quite easily. Of course, this is a good framework even for us, but it also increases the risk for attacker to build such a model for bad use. Then what we want to do is to prevent such a misuse somehow by transforming our speech in advance. Of course, speech have to be still understandable because user want to upload the audio to SNS. So the message and the contents have to be understandable, but we want the attackers to identify you. Can we do this? So that's the goal of speaker anonymizations. Then if it's possible, in addition to the basically protections against attackers, we can also come up several new applications. For instance, nowadays, speech interfaces collecting our voices from smartphone or smart speakers at home, then the audios will go to the cloud. But I don't know what happens on the cloud. Maybe might be okay, but if what happens if information leakage happens? Probably it will be safer if company decided to store anonymized audio and speaker embedding vectors at different places. I think that's safer options. Okay. Then I think we can also use such a voice anonymization filters when we have remote communications. If you need to speak to someone unknown, that kind of filter might be useful. And then how do we evaluate such as speaker anonymizations? This is very good question since this is a new topic and no one defined how to evaluate that appropriately. So we spent some 6 months about the metrics with the French communities because they are quite keen on voice privacy due to EU GDPR. Then we came up some not perfect, but acceptable metrics that we can do right now. So in terms of voice privacy, basically, of course, we want to enhance privacy after the transformations, but user has some motivation to use other tasks. So they are called downstream tasks. So for instance, user may want to use an ASR system. User might wish to upload the audio to SNS to send a message to someone. So they have another motivations. So, and therefore, such a performance on the downstream task shouldn't be degraded. Then here, we chose ASR word error rate as such a performance of downstream task. Of course, you may choose other metrics if you have more specific downstream applications. But I think for the most of cases, ASR exists in spoken devices, and also ASR word error rate can be seen as approximations of intelligibility score. Therefore, as a utility matrix, word error rate is suitable. Then what we want to do is basically we want to enhance the privacy, but we do not want to degrade utilities. If we use a word error rate, we do not want to change word error rate even if we enhance privacy. Then how do we measure privacy? So one possible way is to use a biometric system, more specifically automatic speaker verification system. Then we make sure that transform speech cannot be linked with original speakers by computing equal error rate. Then we also need to consider several types of attackers because attackers may have advanced skills sometimes. So we consider two types of attackers with limited knowledge, which is called OA, and also more like advanced knowledge. So this attacker actually aware of the protection method to some extent, and then they do some like de-identification, a strong de-identification attack by using a part of the knowledge of anonymization system. Then what we propose to do this is basically voice distinguishment followed by speaker masking. The first, we decompose speech into 3 attributes: fundamental frequency, content obtained from Hubert, and then speaker embedding vectors. Then speaker embedding vector would be anonymized. Then we synthesize speech back by using hi-fi gun. This is a neural vocoders. Then question is how we anonymize audio. So basically we use an external pool database of speaker embedding vectors. Then we chose 5 speakers, meaning this similar speaker compared to your ID, your characteristics. Then we compute average by choosing some numbers of speakers embedding vectors average. So we chose dissimilar speakers and compute average, and then replace speaker embedding. By doing that, basically your voice becomes someone else which doesn't exist, but converted speech should be quite different from your original speaker characteristics, and therefore attacker cannot identify you. Because of the limited time, maybe I will skip some details, how we extract content. Basically, we use Hubert, but we did some trick to make content representations to be more useful by attaching some linear projection layer that predict indexes of k-means clusters index. In terms of speaker embedding, we use eCappa TDNM, which is state-of-the-art speaker embedding, by using SSL features. If we simply use this speaker embedding for speaker verification performance on box L1 is 0.87, so which is quite low accuracies compared to state-of-the-art. State-of-the-art number is 0.5, so it's not so bad. Then in terms of hi-fi GAN, which is popular neural vocoders, so basically we concatenate content information's fundamental frequency and the speaker embedding. Then we upsample those informations to the waveform points. Hi-fi GAN has two discriminators. The ones that I will skip the details. I have some tutorials on neural vocoders in the past, and then these tutorials are available on the YouTube. So if you're interested, please see them. Instead, let me show you results and also samples in Mandarin so that you can understand how it sounds to you. Here's the results. So horizontal axis corresponds to word error rate, and then vertical axis corresponds to equal error rate. Then here's the original speech. So low equal error rate, low word error rate. Then we want to increase equal error rate to higher values because we want to protect our privacy. But we don't want to increase the word error rate, because if we increase the word error rate, it causes a problem to the downstream task. Then we compare our method N1, N2 with many other methods, including the ones using broadcasting. You know, the broadcasting also is a kind of anonymization, but it's found that ones using the TV is not appropriate. Attacker can identify original ID if they have advanced knowledge. And compared to that, we obtain about 50% equal error rate, and then word error rate regulations is almost marginal, which is a good news. So let me play some of the sample. Maybe the first one is the Japanese. Please know that training data is English, but since SSL are trained multiple languages, we can input any speech in any languages. You don't need to understand the content, but please pay attention to the speaker characteristics.
次に 2.2 不整合マーカーとしての歯に入ります。では、絵と違い歯の場合にはどのような不整合性をチェックしているの？
次に 2.2 不整合マーカーとしての歯に入ります。では、絵と違い歯の場合にはどのような不整合性をチェックしているの？
けれども、じゃあそんなわざわざ高望みをしないで日本の日本でも演劇があるから見に行けばいいじゃないかっていうけれども、じゃあそんなわざわざ高望みをしないで日本でも演劇があるから見に行けばいいじゃないかっていう
を抽出するときに、 小一問題を解くというほどに帰着されるので、固有語彙というアイゲンフェ
を抽出するときに、小一問題を解くというほどに帰着されるので、固有語彙というアイゲンフェ
Here's the samples in Mandarin. So again, Mandarin speakers or Mandarin speech data are not included in training data set. So this is a zero-shot conversions.
炮兵军士长美国海军陆战队中指挥使用大炮的2级准尉。炮兵军士长美国海军陆战队中指挥使用大炮的2级准尉。
记者随后联系呼和浩特市城市管理行政执法局。
记者随后联系呼和浩特市城市管理行政执法局，
共同探索培养重点骨干文化企业。
共同探索培养重点骨干文化企业。
So I hope the speaker ID has changed. Then, according to automatic speaker verifications, ERs go up to 50%, and therefore, machine cannot tell who you are. All right, so that's the about my presentation today. So I talk about current situation of speech synthesis. Then I mentioned entertainment applications and introduced Rakugo speech synthesizers trained on the Japanese traditional vocal performance. I also mentioned speech intelligibility enhancement. Then I also mentioned speaker anonymization as a new application to protect our privacy. Before we finish, I just want to mention that in addition to these topics, we're also working on other topics like vocoders that integrate DSP and the neural network, and also music applications as well, like MIDI to waveform conversions using TTS, because MIDI to wave conversions are actually quite similar to text to speech by replacing text into MIDI. And also, we are working on predictions of MOS score for automatic evaluations for TTS as well. So if you're interested, please visit our page. I will show you QR code next page. But before that, I will play some piano samples predicted by deep learning from the given MIDI. So basically, we use a transformer and a hi-fi gun to transform the given MIDI to the waveform. And here are the samples to finish off my presentations. Oops. So maybe if you have musical educations, you might spot some errors in very low pitch and high pitch, but actually it's not bad. So we need to handle very long dependency to handle this like a 30 seconds audio. Use some some new techniques called sparse transformer, but we can use basically text-to-speech framework to produce these kind of new applications, because TTS already reaches the human levels, meaning it's a quite good frameworks to sequence mapping. So I think probably you might come up some new applications if you have interesting ideas. Okay, so if you're interested, please go to our website, homepage, GitHub, and then you can go to the website through this QR code. And also, sorry for this advertisement, we are currently hiring postdocs. We have few opening postdoctoral positions in terms of both generative models and also security. So if you're interested, please contact us. Thank you very much.
Okay, thank you, Professor Yamagishi. So any questions from the audience? Yes, please.
Two questions. I'm an NTNU student, a student from NTNU, and first question is, what's your favorite goal? And second, do you think number of queues is also an important part of that goal? Thank you.
Sorry, I couldn't catch the questions. So maybe could you repeat your two questions again?
Okay. The first question is, what's your favorite goal? And the second question is, do you think the number of queue is also an important part of that goal?
Okay. You said my favorite rakugo? Yeah. I start to listen to rakugo, but actually when I start a project, I didn't have such a custom to listen to the rakugo, so I cannot answer the first questions. But instead I could mention the non-verbal cues, which is a very good questions. Rakugo story. Oops. Yeah, rakugo story contained many characters in story. Sometimes actually performer imitate even animals, like a dog, and then sometimes they also imitate very weird situations like a drunk, sleeping. So yeah, there's many non-verbal cues, and then we have to generate such a sound as well. Then one of the clusters in this TSE visualizations, we have clusters corresponding to paralinguistic sounds as well. At this moment, we don't have generation scheme to generate such a paralinguistic sounds. But I mean, last month or 2 months ago or this month, we start to see many diffusion-based models that generate paralinguistic sound or general sound from the text as well. So maybe it might be possible to generate this kind of sound from the models automatically in the near futures, if we have data.
Okay, any other questions?
Okay. So his question was, why did I use a non-autoregressive ones, non-autoregressive TTS? So first of all, my architecture for rakugo synthesizer is autoregressive ones. So this is quite slow. But it's fine because we don't need to synthesize rakugo real time. Eventually we have to do, but as long as we could synthesize rakugo offline, it was fine. And also we care the qualities rather than efficiency. On the other hand, for speaker anonymizations, we use non-autoregressive ones. And this is simply because the architecture is much larger than rakugo ones. We have huge Hubert encoders, huge E-kappa TDNM, and hi-fi GAN. Then they are connected. So we have 3 huge neural networks, and then we have to somehow manage them. Then if we use auto-regressive ones. Of course, you have higher quality, but you have long computational time. And then in this project, we decided to make it efficient because of these huge networks. It's just like a practical reasons. Okay, so you are talking about sequence-to-sequence models, right? Yeah, good questions. Since this Rakugo performance is very long audio, then the relationship between text and vocalizations is more challenging than alignment between speech and the phoneme. Therefore, yeah, we need to do some tricks to make the training stable. I didn't spend so much time, but we, for instance, introduce LSTM self-attentions and two type of attentions in encoder and decoder. That's tricks to make the training stable. Otherwise, we have some attention errors, as you said. But it's not perfect. Sometimes synthesized speech has weird attention errors, like models repeat the same phrase twice and then maybe skip some parts and so on. So that's basically we have same problem as speech synthesizers even for these entertainment applications.
Hello. Okay. I guess we have to keep our time schedule. I think many of you still have some questions. You can ask Professor Yamagishi offline. So I think that the piano part is the most amazing part to me. I will ask my son not start learning piano anymore. We can use computer to do it. Okay. So let's give a big hand to Professor Yamagishi. And this is the end of this session. Okay, thank you.